but I'm very happy to be here. Some of you may not know I'll be spending this whole semester in Sweden. Starting the week after next, I'll be based in Stockholm, in particular at Nordidas. I'm very much looking forward to that and to not having to catch the train. So today, I'm speaking about the application of BCS theory to quantum chromodynamics at very high density, where, as I hope I'll convince you, the application leads to some remarkable insight into confinement, chiral symmetry breaking, and leads to the prediction of a beautiful new phase of matter that hopefully it actually exists in the world in neutron star interiors. And then I will discuss some dynamical properties of QCD at zero density that are relevant to some of the issues that arise also in superconductivity, as well as interesting in themselves because they control, as you'll see, a great deal of QCD spectroscopy. So, why might we expect on theoretical grounds QCD to be tractable theoretically in this limit of large density or large chemical potential and small temperature? Well, there's a principle that I learned from a Jesuit. We had been using it in physics long before, but he learned it in seminary and learned that it was called the Jesuit Credo. And the Jesuit Credo is very important in theoretical physics. And it says that it's more blessed to ask forgiveness than permission. And in that spirit, one often makes the most radically simple assumptions one can and sees if they work or if they break down, if they get internal signs of breakdown. If they don't break down, we declare victory and say that maybe that simple description is correct. So in that spirit, whereas at low density, relatively low density, including nuclear density, QCD is very complicated, we might hope, and not appropriately described in terms of the basic degrees of freedom, quarks and gluons, we might hope that at ultra-high densities we can get away with starting from a quark-gluon description. And in fact, if we take the first steps along that road, it looks very promising. At very high density, one has a very large Fermi surface for the quarks, which means the low energy excitations involve modes that are near the Fermi surface, and therefore quark modes that involve very high momenta. When you have modes of very high momenta, you're starting to get into the regime of asymptotic freedom where the interactions are weak. Taking that even a step further, the important possibilities for scattering of modes near the Fermi surface are into other modes near the Fermi surface. That's sort of the beginning of Fermi liquid theory. And there are two classes, either scatterings that involve large transfers of momenta, and then asymptotic freedom really does apply, and you have a weak coupling. So one can attempt to perturb consistently around this starting point, or the scatterings are through small angles, but if they're through small angles, they don't do very much. So we might hope to get away with ignoring those too. So that's the apparent simplification. And in the early days of QCD, people thought that at very high density, you would essentially be able to describe things in terms of just non-interacting quarks to a good approximation. But if you try to take that a step further and see if it's internally consistent, if you try to really calculate corrections, you quickly find that there are infrared divergences. And there are two sources of infrared divergences. One is simply that everything I've told you so far has to do with the quarks, the Fermi Pauli exclusion principle and Fermi statistics that limits the possible interactions of quarks. It says nothing about the gluons. And the gluons, although at high density, they're electrically screened because we have a high density of charged particles, namely the quark. They're not magnetically screened, and in fact, when you study the magnetic interactions, you get infrared divergences. Also, there's a more subtle problem, which will turn out to be actually the solution, which is there's another source of divergences. I told you that the scatterings near the Fermi surface have a small coupling. However, there are lots and lots of degenerate states. If you take pairs of quarks with momentum p and minus p on opposite sides of the Fermi surface, they all those configurations have the same quantum numbers. They have zero total momentum and close to zero energy because you don't need to excite them very much to get from an occupied to an unoccupied state. And so you're doing degenerate perturbation theory. And as is well known, when you're doing degenerate perturbation theory, even small interactions can lead to qualitative changes in the nature of the ground state. And in this particular case, there's a famous instability of that kind. That's namely the Cooper instability to attractive interactions near the Fermi surface, rearranging, even if they're very small interactions, rearranging the ground state from something that contains low energy excitations into something that has a gap into a superfluid, or if the material is charged, a superconductor. That sounds promising or intriguing also from the point of view of QCD, because the main phenomena of QCD had direct analog, so in terms of the main phenomena of superconductivity, and vice versa. What's called the Meissner effect in superconductivity theory, the fact that interactions become short range, or at a more abstract level that the photon gets a mass, is essentially the same as the phenomenon of confinement in QCD. Namely, the gluons no longer mediate long-range forces. There's no long-range effect of the colored charges. That might sound like an abstract and wimpy version of confinement. We'll get to more familiar kinds like non-existent diffractional charge a little later. And the other main phenomenon of QCD is the fact that the quark spectrum has a gap, or chiral symmetry breaking, but of course that also has a direct analog in superconductivity, where the energy gap for the fermion excitations is the central phenomenon. The BCS theory of superconductivity is very hopeful in the context of QCD at high density, because it's a technique that exploits the weak coupling, and here we really do have a weak coupling, as I mentioned, and it's non-perturbative, so it can mediate, can give theoretically phenomena like the Meissner effect and the gap, which, in other words, would give confinement or chiral symmetry breaking in the context of QCD. So these phenomena, which in general are very intractable, hard to get a grip on in QCD, become approachable and, in fact, demonstrable and easy to calculate. But easy is too strong, but possible to calculate. So, with that introduction is what to make it plausible that one should get analogs of superconductivity phenomena in high density QCD. Here's a more detailed approach to that phenomenon. So first we need an attractive interaction. In the theory of metals, in the theory of superconductivity in metals, that was a very difficult thing to obtain because the primary interaction between electrons is, of course, the Coulomb interaction, which is repulsive. To get an attractive interaction, you had to get into subtleties of phonon mediation and retardation and so forth. But QCD in this regard is actually much simpler because the primary quark-quark electric interactions can already be attractive. This is because in QCD, unlike in QED, you can have wave functions that are antisymmetric in the charge, in the color charges. So when you have two triplets of color charge, they can be anti-symmetrized into an anti-triplet. If you have two quarks and put them in the anti-triplet state, then as they come together, they have the same electric flux coming out as would one quark, the same magnitude of electric flux. One quark is a triplet. So you have the electrical energy by bringing the quarks together in that channel. Therefore, it's an attractive interaction. You can also, of course, calculate directly that it's an attractive interaction. And more sophisticated treatments, including things like instantons, give the same result. So the totally antisymmetric channel. Then we have to, so that's the color wants to be antisymmetric, and we get some interaction with that. If one wants to discuss what the spin likes to do, what's the most attractive way of forming Cooper pairs, if you like, of quarks, then you have to investigate the magnetic interactions, and that's more subtle. I could make intuitive arguments, but let me not. Just to say that the result of the calculation is that the most favorable channel for the spin interactions is that they should also be antisymmetric. In other words, that the quark pair should form spin singlets. I will show you later in the talk very impressive direct phenomenological evidence that this is the attractive channel in between quarks in QCD, and that phenomenon controls a lot of the spectroscopy in QCD. Well, because we want then, we still have, the quarks of course are fermions, so we have anti-symmetry in color, anti-symmetry in spin. We have to get one more kind of anti-symmetry in order to have an acceptable fermionic channel. We can avoid paying the price of excitation in angular momentum of going to P wave. We can stay in S wave as long as we pair different flavors of quarks. So we can have U and D quarks or U and S quarks. And so that we can have something totally anti-symmetric with all these internal quantum numbers, leaving the spatial wave function symmetric. But because the flavor plays a role, the number of flavors is important, it turns out that with two flavors, you get a result which is complicated. The condensate wants to form between the U and the D quarks, because it's anti-symmetric in flavor, you need the U and the D. And when you anti-symmetrize in flavor in spin, you have only 1 degree of freedom left, because it's a singlet. And then when you've anti-symmetrized the flavors, there's only 1 degree of freedom there too. And so the color pairing makes a triplet, makes one preferred direction in colored space. And so when you have a condensate, a residual SU2 gauge symmetry is unbroken, which means that not all the quarks have a gap, which means that there are still infrared divergences. So I won't say anything more about the SU2, the two-flavor version. although it's very interesting theoretically, and would play a role at intermediate densities where the strange quark mass is important, and it's a good approximation to just work with the lightest two quarks. At higher densities, where the strange quark mass is negligible, then you get a much simpler and more beautiful theory, as you'll see, and that's the case I'll be discussing in the rest of this lecture. So I'll be neglecting the strange quark mass. In that case, the channel that's favorable is very elegant and gives rise to the phenomenon of color flavor locking. Suppressing the spin and momentum indices at first, just to display the essence of the thing, we have color indices and flavor indices, like that, on the quark fields. And the condensate that will turn out to be favorable has the color indices and the flavor indices matching like this, tied to each other by Kronecker deltas. We call this color flavor locking because in the presence of such a condensate, one no longer has symmetry separately under color rotations or flavor rotations. The Kronecker delta would be a vector under the color and also a vector under the flavor, but you do have residual symmetry when you simultaneously rotate both color and flavor, both of which are SU3. So you have 3 colors and 3 flavors. And that's, by the way, why 3 is important, because 3 equals 3, whereas 3 does not equal 2. So the 3 flavor theory is a lot simpler. It has a more elegant possibility for pairing, which turns out also to be energetically favored. So, to say it a little more formally, we start with color SU3 cross left-handed flavor SU3 cross right-handed flavor SU3. The chiral symmetry is, left and right hands of quarks can be treated independently if we neglect their masses. So we have chiral symmetry separately on the left and right. By this kind of condensate, that gets broken down into just a diagonal SU3 where you have to rotate all of them at the same. Okay, it's only this diagonal subgroup that leaves these Kronecker deltas invariant. So the left-handed chiral condensate would be happy to rotate with the color, but the color symmetry is a vector, demands that we rotate the left and right the same so that they both get locked to color, and therefore the left and the right are no longer independent recipient. To make this invariant, both of them have to rotate together and rotate in the same way as color. Then, of course, the Kronecker delta is famous for being invariant under rotations of the total group. This phase of QCD, or this phenomenon of color flavor locking, is analogous to what happens in the B phase of helium-3, where in that case one locks not color and flavor, of course, but orbital and spin degrees of angular momentum of the atoms in helium-3.
If we compare with the helium, how does the condensate knows what bases to choose compared to the flavor sector?
It doesn't know because you. Oh, sorry. I guess. Well, let me go to the next transparency.
Okay. Because in helium, it is
the dipole. Yeah. So in this case, the residual symmetry is a real, honest-to-God symmetry. It's not. So it's. This controls the whole twist. It goes back by whole pages. But full of them. Yeah, oh, okay, that's what I want. Here. This symmetry is for real, it doesn't mean real. more formal version of what I said in words on the previous slide. So we have the ground state that I displayed, where the condensate looks in flavor and color like a delta function, but here I haven't suppressed the spin indices. The spins go into a singlet like that. So that makes a spin 0 state. And furthermore, I've also displayed the momenta. So it's K and minus K that pair. The condensate or pairing amplitude is dependent on the absolute value of the momentum only. That's because we chose to make it S wave, not P wave. And this will be a function when you compute it that peaks near the Fermi surface. That's where the pairing is strongest and falls off away from the Fermi surface. Furthermore, to make a true spin singlet, you have to pair just left-handed quarks. And the right-handed quarks have an equal and opposite condensation. It's with that equal and opposite condensation that parity is conserved. I won't get into such fine points here. V1 is much, much bigger than V2 when you calculate, and that reflects the intuition that the pairing should primarily be in the color anti-symmetric channel. So this one turns out to be 6 to 10 times as large as that in typical model calculation. Now, to address your question, this was a particular choice of the alignment of the colors and flavors. There are other equally good, from the point of view of energy, directions of condensation where we have a different alignment, and I just parameterize those alternative ground states by this matrix U. So each of these has the same energy as that. There's a symmetry what's called a spontaneously broken symmetry, of course. You can start with any one of these and you'll get equivalent physics, but they're distinct. So that's the structure of the ground state, and I should say, I won't be displaying the calculations here, but since it's a weak coupling problem and one knows exactly what the microscopic interaction is, you can assess different alternatives for the pairing. This was just one motivated guess. It turns out to be a very good guess. This, for all the competitors that have been examined, this particular kind of pairing with color flavor locking and complete anti-symmetry has by far the best energy. So let's now look at its consequences. And the consequences that are of interest are, what are the low energy excitations around this ground state? That will control the phenomena that are accessible. There are three kinds of elementary excitations. There are the elementary excitations formed by the quark fields. There are the elementary excitations that you get out of the ground state by hitting it with the gluon field. And then there are collective modes, Nambu-Goldstone modes, associated with the fact that we have a spontaneously broken symmetry. If you look at the quantum numbers of these modes, you get a very remarkable surprise. If you look at the things that a quark field produces, they turn out to have the quantum numbers of the physical baryons that you would find in the particle data tables. That sounds very odd because baryons are famous for being formed from three quarks and also for having no color, whereas quarks have color. But let me explain how it happens. First, if you look at a quark field, it has a color index and a flavor index. But in this residual SU3, that's still a symmetry, in the color flavor lock state, you have to rotate both flavor and color together. So under that SU3, you have the flavor index and the color index of the quark rotating together, which means it forms an octet plus a singlet. The singlet turns out to be heavy, the octet is light, and of course in the particle data book you will find an octet of baryons, which are spin 1/2 objects. I'll show you how the electric charges work later. But let me remark about this apparently unbridgeable dichotomy between baryons having 3 quarks normally, and on the other hand, having them being produced from a single quark field. It seems that it's very difficult to make 1 equal to 3. However, it's not so difficult to make 1 equal to 3 when the vacuum is filled with pairs. It's filled with quark pairs that are made out of 2 quarks. You go with the 2 quark operator from the ground state back to the ground state. And so, if you can add 2 quarks for free, the quantum numbers of 2 quarks for free, it's no longer impossible that a baryon can be, something with the baryon quantum numbers can be produced with a single quark field. And that's what happens. Similarly, the quantum numbers of the gluon field, which start out both to be colors, when color is locked to flavor, can also become indices that transform under this residual SU3 flavor group, which the new SU3, the diagonal SU3, which is the remaining symmetry, the global symmetry of the state. And so the gluons have the quantum numbers of the vector mesons that you find in the particle data table. And then finally, the collective modes associated with chiral symmetry, with spontaneous symmetry breaking in general, here with chiral symmetry breaking, have the quantum numbers of the particles that are famously interpreted as collective modes of chiral symmetry breaking, namely the pseudoscalar meson ions, kaons, and the eta particle in normal QCD. So these also have the quantum numbers of a low-lying excitation in vacuum QCD, or the version of vacuum QCD that you would have expect to have with 3 massless flavors. So altogether, we get a complete match between the low energy degrees of freedom and their quantum numbers that we can calculate in this state, and the low energy degrees of freedom that you find in the particle data group tables experimentally at 0 density. Since the spectrum and the symmetry nicely match expectations for a nuclear phase of 3 flavor QCD, we conjecture that in 3 flavor QCD there's no phase transition as the density is increased. So, whereas in 2 flavor QCD you have a big difference between nuclear matter at low density, and then you push it up, you get, and bring in the strange quark now, you get to this very different phase. In 3 flavor QCD, theoretically there's no phase transition. This is, I think, very, very interesting from a theoretical point of view, because it means the form of confinement that we can calculate from BCS theory, the form that you get with the Meissner effect and the superconducting gap, the forms of confinement that you can calculate using these weak coupling techniques, are not different fundamentally from the forms of confinement that are famously mysterious in low density QCD. There's no phase transition that separates them. And in particular, as we already mentioned, a quark at high density, something that's clearly a quark at high density, can go smoothly into something that looks clearly like a baryon at low density. We have quark-hadron continuity. Now, as I mentioned, the form of confinement that I discussed may seem kind of wimpy and abstract, namely the absence of long-range forces. When you think of confinement from an experimental point of view, you usually think of the absence of fractional charge. But let me show you that really the absence of fractional charge is encoded in this too. So let's couple in electromagnetism. And at first, it looks terrible. Electromagnetism couples to the different flavors. It couples with charge 2/3 to the up quarks, minus 1/3 to down and strange. So it couples directly proportional to a flavor, to these flavor quantum numbers. But the flavor symmetry is broken. So it looks like electromagnetism is broken. That doesn't look at all like low density. However, we have to be more careful. There's also the color symmetry getting broken. And a certain combination of the two turns out to be unbroken. So the unbroken gauge symmetry is a combination of what was originally electromagnetism and what was originally color. But it's that combination that corresponds to a massless gauge boson that doesn't get lifted by the Meissner effect, or Higgs effect. And it's that which is the photon in this material. That's what you would interpret as the photon in this material. So when we say measure the electric charge, we really should ask the photon what it thinks the electric charge is. And we have to take this combination to determine what the photon is. This is similar to what happens in electroweak physics in the standard model, where you start with SU2 cross U1, a weak isospin cross hypercharge, and both of those are broken when the Higgs field requires a vacuum expectation value, but a certain combination remains unbroken. That's what becomes electromagnetism. And the charges of the quarks and leptons are quite different from their hypercharges. They get rearranged because of this integration process. So exactly the same thing happens here. Here it is concretely. So the original photon up here acted in flavor space with charge E and then 2/3 minus 1/3 minus 1/3 for up, down, and strange. There's a flavor generator in SU3, a color generator in SU3, which has exactly the same form, but of course with a different coupling constant. And if we take this combination, G times this one plus E times this one, and normalize it, that will annihilate the ground state. That'll be an unbroken symmetry because it'll annihilate all those Kronecker deltas. Because you'll have one index, the upper index will be a flavor index, the bottom index, the color index, and they're rotating in the same way. So the Kronecker delta is left invariant. Okay, so this tilde object is the photon inside the material. And now we can count up and see what the electric charges are. Let's do it, say, for quarks. Quarks have one flavor and one color index. So we have to pick a flavor index and a color index and calculate the charge. So let's choose the up quark, which has, say, the middle color. That's the red, white, and blue, so white. The white up quark. So it gets E times 2/3, G times 2/3, G times E times 2/3 from this guy. And then plus, because it's on a lower index, G times E times minus 1/3. Minus, because it's on a lower index, G times E times minus 1/3 from its color index. We put flavor on top and color on bottom. So altogether you get E times G divided by this square root times 1. And you can easily convince yourself, following the same logic, that no matter which combination you take, you're going to get either 1 or minus 1 or 0 times that same unit, G times E divided by square root of G squared plus E squared. Now let's look at the electron to get the unit of charge. If we look at the electron, it sees just electromagnetism. Its charge, of course, is minus 1. So you get only a contribution from here, which is minus EG divided by square root of G squared plus E squared. It's just minus 1 times that same basic unit. So the quarks and the baryons, which are the things produced by the quark fields, all the low energy excitations have integer multiples of the electron charge inside this material, which is the famous criterion of confinement. You shouldn't see fractionally charged objects. So even though you see quarks, they're not, in a sense, they're not fractionally charged, and they don't come labeled quarks, so you could be fooled into thinking they're baryons. They are. And you can do the same exercise for gluons and for the nebulas and bosons. For people who are even older than me, they may remember the Han-Nambu assignment for quarks, where Han and Nambu wanted to preserve integer charges for quarks. Well, it turns out to be exactly true at high density. Their scheme for getting integer charges for quarks is essentially the same scheme that's picked out dynamically at high density. Let's discuss the material that we've got by this reasoning. It's not a superconductor in the ordinary sense. We just showed that there's a massless gauge boson, which is mostly photon, mostly the old photon. Since G is much bigger than E, this is mostly the old photon, in some sense. And it's massless. So we do have a form of electromagnetism in this material. Right? We have electromagnetism. A photon coming into this material would be partially reflected, but would have a large amplitude to get in. Because it matches, the photon outside matches quite well the photon inside. So in fact, it's the world's best insulator because it has a gap, and the gap is characteristic of QCD scales, not with the chemical scales. So it's the ultimate high temperature insulator. Nevertheless, it's also a superfluid. It's not a superconductor, but it is a superfluid because there is a continuous symmetry that's broken, an exact continuous symmetry, namely, remember what condensed was two quark fields, and those things have non-zero baryon. So baryon number is spontaneously violated, just as it is in liquid helium-4, and the phenomena that correspond to that are the phenomena of superfluidity. I already mentioned that it becomes a transparent insulator. Transparent because there are no low energy charged excitations. It's also, going back to realistic QCD for a moment, it's also clearly drastically different from nuclear matter, which is the lower density state in realistic QCD. This is the asymptotic state at very high densities. Since it's so different, one might expect first order phase transition between the two that could be accompanied with a drastic change in density. And calculations, although they're not rigorous or controlled, seem to suggest that there is, at the interface between these two materials, perhaps a change in density by a factor of 5 or 6. So the neutron star has a very drastic change in density over very, very tiny distances. And that is the hope of making connections with phenomenology, because such a drastic change would affect the moment of inertia, the radius versus mass relation for neutron stars, and so forth. At present, no neutron star has had a measured mass. Has had a measured radius, but there are prospects that that will improve in the coming years. So that's the discussion of color superconductivity. This is a logical place to stop and take questions. If there are any questions about that, before I change gears a little bit. Well, there are two different models. One model is not a model. One model is just QCD. And then, well, you can calculate directly in QCD that this is the most favorable channel at asymptotic densities. So that's not a model. That's it's a model in the sense of the standard model. However, of course, that's asymptotic, and we're interested in the phenomenological applications. And also, to make the calculation simpler, one often uses what's called the Nambu-Jones-Lucinio model, which is basically a 4-fermion interaction which has all the appropriate symmetries of QCD, but is not QCD. And then there's even another level of abstraction, which is like in the original BCS theory, just to take the pairing interactions near the Fermi surface and throw out the and all those things are equivalent and correct at ultra-high densities, but they differ in tractability and in plausibility and intermediate density. But fortunately, they all, well, at asymptotic densities, they all agree that this is the best state and by a wide margin. Okay, so, but your question actually leads very naturally into the next topic, which is, all right, that's what happens at ultra-high densities, and where the relevant interactions are the weak interactions that one has in QCD between high momentous states. What happens at low and intermediate densities that are plausible for the outer regions of neutron stars, and certainly also in vacuum. Can we see any vestige of this pairing mechanism and this attractive channel in existing phenomenology? And I want to argue that the answer is yes, and that it's a very fruitful question and answer. So we want to study the forces between two quarks experimentally. Since quarks famously can't be isolated, we have a fundamental problem in trying to isolate two of them and study their interactions. But there is a way of getting to that, which is to spin them around, or having baryons, which are made of 3 quarks, spin around. If they're spinning, then by centrifugal forces, one quark goes to one side and the other two go to the other side. And so one side, the side with 2 quarks, makes a nice laboratory for studying quark-quark interactions. We can study which quantum numbers are favorable for that pair of quarks in particular, to see if this totally anti-symmetric channel really is favorable, and by how much. Now, this study was mainly I did with Alex Selim, and we started because we wanted to look at the cleanest case. We looked originally in the back of the particle data book at the highest available angular momentum variable. And we got very nice results. So we were tempted to go down from L equals 7, I believe, was the starting point, to L equals 6, and it still worked very nice. So we went to L equals 5, 4, and then nothing stopped us. We went all the way down to L equals 0. As you'll see, a few simple ideas work remarkably well to organize the vast bulk of QCD spectroscopy. So here are the three ideas. One is what's called the Regge or Chew-Crouchy mass formula between the orbital angular momentum of a meson or baryon state and its mass. This is the relation you get for more mechanically. I mean, they inferred it from guesswork and phenomenology and some shady arguments. It's also, you can also get it by slightly less shady modern perspectives by saying that it's what you get if you have essentially massless quarks connected by a string of constant tension and spin it around. Then the string stretches, and if you see how much energy is associated with that stretching, that's the only energy there is, you get this linear relationship between angular momentum and mass squared. This sigma is universal. It's supposed to be the same for all mesons and baryons. A is a residual intercept, which is different for different families of mesons and baryons. It's supposed to be due to zero-point motion or internal structure or excitation of that string. I won't go into details, just to say sort of fudge factor. That's, of course, it's only important for small l. With a basic idea of how to break them down. So that's one hypothesis. Another hypothesis is weak spin orbit forces. So we're going to, this is just to say we're going to ignore spin orbit forces. And then finally, the crucial distinction from the point of view of this talk and what we were after in this investigation is the distinction between the quantum numbers of the two quark states that you isolate in baryons and put on one side of the string inside your baryon. And these three principles or properties, which are only very qualitatively and not quantitatively motivated from QCD, very poorly understood fundamentally, but they work remarkably well to organize the spectroscopy now, even down to low end. So this is the theory which I outlined at the beginning, and I will only go through very quickly. Color minimization suggests that the correct way, the most favorable way to put two quarks together is in the color anti-triplet. Both one gluon exchange and instanton suggest that. Furthermore, we want to pin down the spin. That requires looking at magnetic interactions, and that study shows that the more favorable one is anti-symmetric, the spin singlet. So we'll call these the good diquarks, and these guys with the bad value of the spin, the bad diquarks. Since this distinction is magnetic, we expect it to be most important when the quarks are most relativistic, and so for the U and D quarks, a more powerful effect quantitatively than the strange quark. And then finally, because correlations are important in getting these particular quantum numbers for a pair of quarks, if we try to force two diquarks to get two good diquarks together, we'll find conflicts. We won't be able to maintain good diquark quantum numbers between every pair of quarks, so that will tend to give repulsion between the good diquarks. So here in pictures is our model of mesons and baryons, and also one more suggestive thing. So we have on one side of our spinning string either a diquark or an antiquark. Either of these is a color anti-triplet. On the other side, to balance the color, we have either a quark or an anti-diquark. So diquark quark gives a baryon, anti-diquark quark gives an anti-baryon, quark anti-quark gives a meson. And the other possibility is diquark anti-diquark. And that gives something very interesting for future experiments. It will get quantitative predictions for tetraquark states with 2 quarks on one side and 2 antiquarks on the other. And then you just take that, ignore spin orbit forces, ignore all possible complications, just spin it around and use those 3 principles. So I won't attempt to show you how all of hadron spectroscopy gets subsumed into this scheme to a remarkable extent, but I'll just show you the case where there's the most data and then another instructive cut of the data. So most data, of course, is in the channels that you can get by studying scattering off nucleons. So in channels that are zero strangeness baryons, these things are accessible by pion-nucleon scattering, or for that matter, nucleon-nucleon scattering, or photonucleon scattering. So there's an enormous amount of data on them going back to Fermi. And so many, many states and resonances have been discovered. There's a sort of self-consistency procedure in deciding where these states go. Of course, they don't come with labels that tell you what their orbital angular momentum is, or for that matter, which kind of diquarks they contain. To get the orbital angular momentum, we use that Shu-Fauci mass formula. And of course, the whole thing might not work, but if we find consistent assignments, we keep going in the spirit of the Jesuit credo. And then the only other thing we're supposed to take into account is whether we have a good diquark at the end or a bad diquark. If we're dealing with zero strangeness, the only way to get a good diquark is to have, since it's anti-symmetric in flavor, is to have an isosinglet. Also, if it's a good diquark, its spin is anti-symmetric, so it's a spin singlet. So the good diquark has very characteristic quantum numbers. It's always an isosinglet and always a spin singlet, whereas the bad diquark is an isotriplet and a spin 1. And so the things that you can get by putting together a good diquark and a quark on the other end have different quantum numbers than what you get by having the bad diquark and a quark on the other end. And you can distinguish them by quantum numbers and then see if it's really true that the mass of the good diquark is less than the mass of the bad diquark. So the good diquark will contain only isodoublets, because one side of it is an isosinglet and the other side is an isodoublet. So you don't get any of these deltas, the iso 3/2 states. I guess they're quintuplets. No, quadruplets. And then the other prediction is that nothing else matters. So the remaining states, although they have different relative alignments of the spins of the quarks and diquarks relative to each other or relative to the orbital angular momentum, although they'll have different observable quantum numbers, should have almost the same mass. You get a massive degeneracy of those guys. So you get a few degenerate antiquarks, good diquark states, and many degenerate, heavier, bad diquark states. And sure enough, that's the pattern that emerges. If you look especially at the higher angular momenta here, although the data becomes sparse. Let's look at just 1 and 2. You find these, a pair of iso-doublets with low total spin here, with considerably smaller mass and almost degenerate than the rest of the nucleons and deltas, which have a variety of quantum numbers, typically larger values of the observable total angular momentum. The parity is also predicted. I'm sloughing over details here, but you see they're all roughly degenerate and also all well split from a good dipole. And that's even clearer in the L equals 2 when you start to get a cleaner separation between the two sides of the string. You can study also strange baryons and also mesons with and without strangeness in the same way. So there are many tables, but just to organize this discussion, let's look at, so to compare apples and oranges, as opposed to apples and elephants, we take all these different states with L equals 2. Okay, so these are the zero strangeness baryons. These are zero strangeness mesons. These are strangeness 1 mesons. These are mesons believed to be made of S and S bar. And we have singly stranged baryons and doubly stranged baryons. Now, let's notice the characteristic things here. As mentioned before, there's a clear distinction between the masses and of course the consistent quantum numbers for the good diquarks, which are almost degenerate, versus the bad diquarks, which are also almost all degenerate, but not degenerate with the good ones. If we compare mesons and baryons, we find that the good diquark, that they're almost degenerate. See, this is 1680, 1720. The corresponding mesons, which are quark and diquark on the two sides, versus diquark-quark, that they're almost degenerate. In fact, some of the mesons are lighter. So that indicates that 2 quarks can weigh the same as 1, namely the good diquark has about the same mass as a single quark, single diquark. As an aside, theorists who are interested in large N approximations start from the picture that mesons and baryons are completely different kinds of objects. Baryons are supposed to be solitons and very, very heavy. Mesons are supposed to be simple states that are very, very light. You have a lot of explaining to do if you try to reconcile that. Here, if you go to the strange sector, you notice the same thing, that the good diquark baryon weighs almost the same as the meson. So this is a baryon with a good diquark on one side and a strange quark on the other. That's the lambda. It's iso singlet. That's how you can tell. And it has not very different mass than these strange mesons, which are, of course, strange, single strange quark, single quark, single light quark, and strange anti-quark on the other side. When you do all this fitting, there are a couple of things that stick out, so I think those are experimental errors. So this should be remeasured. Because so much works, the things that don't work are suspicious. So either there's something very interesting about it, or it's wrong. I would bet it's wrong. When you go to the strange quarks, They're less relativistic. We would expect different distinction between different spin configurations to be less. And you'll see up here that the good diquark configuration, although it's more favorable than it's actually there are several now with more flavors. There are several kinds of there are bad diquarks and very bad diquarks. In any case, the distinction is less quantitative than it was. So the binding energy involved in these spin forces is less quantitative than it was in lighter, non-strange quarks, which is what was anticipated. So, the quantitative enhancement of good-bad diquark distinctions at large L, we saw these things are pretty much neglected in traditional ground state spectroscopy, which is L equals 0. At large L, they get very clear, where large means 2. 1 is a little less clear, and it really becomes very clear at 2. But then the data runs out pretty much. Is broadly consistent with theoretical expectations, namely that things get, that it's a relativistic distinction, and I don't know why I said correlation-based repulsion. There's some reason. So, the pairing channel that was assumed to be favorable, and actually also calculated to be favorable in QCD at high density, this totally anti-symmetric channel for Cooper pairing that leads to color flavor locking and all those phenomena, is broadly confirmed in even in this in the low energy data. You can see remnants of it when you properly analyze the low energy data. And the scale is quite large on QCD scale. A couple of hundred MeV split the good diquark from the bad diquark. So I suspect that the color flavor lock state, which we can prove to be asymptotic, is actually achieved at fairly modest densities. And there's a chance that it exists in the interior of neutron stars. To do much better from pure theory than these semi-qualitative indications of where asymptotally sets in, we'll need new ideas. Best would be if we could calculate numerically. Many things are calculable in QCD numerically using the techniques of lattice gauge theory, but this isn't one of them. Nobody knows how to do practical calculations at high density in lattice QCD, and that's, for a young theorist, that would be a great triumph to figure out. Also, in that same vein, we found in the study of spectroscopy that the simplicity of QCD spectroscopy seems to emerge at large L, suggestive of some kind of effective string theory that sets in already at very modest values of L, but in any case, that the simplicity sets in at large L. Unfortunately, and to firm that up and play with it, we would very much like to have numerical data that allowed us to not rely on these very difficult experiments that have lots of holes in them, but also allow us to vary the quark masses and things like that to see that the theoretical ideas were correct. Unfortunately, we don't have the existing techniques run out of steam at large L, and that's another outstanding theoretical challenge in the future. We look forward to dialogues with nature experimentally, with experiments on cold atom systems, where you can, to a large extent, dial your Hamiltonian, so you can make something close to some of these model Hamiltonians using cold atom systems, and in neutron stars, and of course, in more precision Hadron spectroscopy. So thank you very much.
questions?
Yeah.
Could you comment, you mentioned it briefly, but this I think is an important question, about the processes of scattering at small angles
Yes.
in the Fermi circle. Because apparently those, well, there is this standard argument in the Landau theory of fermions that those processes are suppressed by the phase volume considerations. But on the other hand, they are enhanced by the Riemann coupling constant, which becomes large at this angle. So how do those two factors into each other?
Well, the running of the coupling is only logarithmic, where the phase space is parallel.
Before you keep the strong coupling here,
Yeah, strictly speaking, we don't know. So we invoke the Jesuit principle that it's more blessed to ask forgiveness than permission. Just go ahead. We can construct this alternative state. Once you, of course, once you're in the superconducting state, it no longer arises. There's a gap. There are no infrared divergences. So what I can say for sure is that that state seems internally consistent. It doesn't have any divergences or instabilities. There's a convergence as well. There's a standard perturbation theory that's well behaved around it. Strictly speaking, can we prove it's the ground state? No. Any more than we can prove analytically that we have confinement. We just hope for the best. If we're getting nice pictures that are internally consistent, then at least that's a possible way things could go. And maybe that should be
So, can you comment on the cold atom systems? What would you like to do in that?
Well, the kind of questions that come up are really, if we want to study the non-asymptotic state, and there are many things one might do. If you want to talk about it seriously, we should discuss it privately. But the kind of questions that come up, for instance, are in QCD at not asymptotic densities, where you can't neglect the strange quark mass. Then, if you have a chemical potential for baryon number, which is what you have in a star, just consider having a chemical potential for baryon number, then the Fermi surfaces of the up and down quarks and of the strange quarks will be of different sizes. Nevertheless, you'll want to pair because there are still these attractive forces. So you have a kind of interesting situation where BCS theory doesn't apply directly because there are different sizes or in its normal form, because there are different sizes of Fermi surfaces. On the other hand, there are attractive forces that you'd like to take advantage of. So different kinds of states have been proposed as candidates for what might happen in that situation. You have mismatched Fermi surfaces. That arises very naturally in high-density QCD, when it's not asymptotic. It also, of course, very naturally arises in fermionic cold atom systems because, well, generally you have to work very hard to make these Fermi surfaces of different things equal. So exploring the states that are actually assumed in those cases will allow us to check some of the approximations and models that have been used in QCD, see whether we got it right. Also, if we've thought of things that other people haven't in the past. So that's the spirit of it. Then there are many more detailed things as well.
Is the relation of these ideas you explained in the beginning to order these moments down to a nice effect?
The relation is very obscure because there's nothing dual about this. This is just Meissner. Right. This is really for electric charge, not magnetic charge. Right. It's really different. It's not. Of course, it's meant for a different regime, so it doesn't necessarily contradict the other one, but it's quite different. Yeah.
I remember it was an old paper, I think, by Gary Goldstein, was using a model very similar to your difork model, you know, assuming
Yes.
this linear thing and difork and quark and working out. Do you know about that?
No, but I'd be very interested to see. It's a good model.
They worked out in some detail.
Yeah, I'd be very interested to see if they reach the same conclusion. One thing I should say, that most of what I've discussed here, aside from the diquarks at the end, is, except for a few details, things that were done 3 or 4 or even 5 years ago. A lot has happened since then, but since I had to start from scratch, I assume I should start from scratch. I couldn't get to the very latest work and keep it comprehensible. But for anyone who's intrigued by these things and would like to know the state of the art, there will soon be a comprehensive review paper by Alford, Rajagopal, Thomas Schaefer, and I think another author that's going to appear, and that is intended for reviews of modern physics. So if you'd like to see the later developments, that would be a very good place to start.
Maybe rather nasty question, I think. But so this is a nice theory, but in terms of, for example, astronomical observations,
Yes.
what are you expecting any specific predictions?
Well, there are no very clear predictions at this point. The closest thing to a simple prediction that's clear, I would say, is this prediction that plausible possibility that there's a drastic change in the density profile of the neutron star. Since we don't know exactly quantitatively what the parameters are, we can't be very quantitative about it. But it should be obvious, I would think, if once you start to study mass versus radius relations for neutron stars, and in particular when you can start to study gravity waves emitted from them when they get excited by other neutron stars or black holes spiraling into them. We'll start to get a handle on the density profile and see if it does have this kind of discontinuity. There are other more subtle ones. I myself haven't kept in touch with this, but that review paper is full of ideas about astrophysics tests. As far as I know, none of them is really both sound theoretically and clear experimentally. Certainly not yet. Yeah.
Try to write down simple phenomenology in terms of Ginsburg-Landau.
Yes.
What would be the function of, let's say, would it be the same or different from kind of standard superconductivity?
Well, it has lots of indices. Lots of indices and lots of fields that couple to those indices. Other than that, it's similar in spirit. And because of the indices, you can form lots of invariants. And if we didn't have a fundamental theory that allows us to calculate many of those parameters, we'd have a real mess on our hands.
So essentially it would be, let's say, non-trivial electrodynamics with several colors, let's say.
Several colors, flavors, spins, right. I've just been playing with superconducting graphene, which also has several indices, but this was a very, very good preparation for that. it might be frightening if you encounter suddenly order parameters with 8-fold indices, but there are many disapplications. Helium-3, of course, also has a lot of indices, so that's similar in spirit. But there, of course, it took a lot of experimental guidance to sort things out, to the extent that happened.
Thanks.